Hi, in this short video we will be talking about planes and other low-dimensional subspaces of higher n-dimensional space. In this class we will commonly be working with n-dimensional spaces, where points are described in n dimensions. For example, we can have a vector x, which is equal to some, let's say, three-dimensional space, x1, x2, x3. And we denote this as living in R3. So oftentimes we will be interested in vectors which live in a separate subspace of this higher space. So to explain what I mean, let me draw a picture. So here's R3. Our vector here might live over here. This is our vector, but we are actually going to be interested in those points which are described by some linear relationship. For example, we could have a plane, which is all the points which fit on this slice. In two dimensions, color this in. In two dimensions, we might have a line. Here, this could be described by, say, the plane z equals 3, and x and y are free to be whatever. And in this case, this would be described by the line y equals 1, for example. So this becomes particularly relevant in machine learning when we want to be able to describe the way that points are arranged in the space and what side of the space they fall on. For example, let's look at a simple example. Where we're trying to draw classification boundaries. So in this sense, we can have some points which are x's, and some points which are o's. And we want to ask ourselves, what is the separating hyperplane, or by hyperplane I mean a line here is in n-1 dimensions, that separates these two sets of points. So here we might find a line here which separates our space. And so on either side of this plane, a line in two dimensions will fall our data points. So here we can say for everything less than this plane, on the other side of this plane, these are all o's. And on the other side, they're all x's. And that's one of the decision boundaries that we'll be trying to find in machine learning. So how do we define this line? And here we just wrote this out as z equals 3 and y equals 1, but there's actually a particular definition in which you can use to define what a plane is. And particularly, you want to define a linear relationship between the dimensions that satisfy all of these points being on this surface. So let's say that we have a plane here. So let's say defining a plane. If we have a plane in, say, 3 dimensions, let's draw it over here. We define this plane as having a normal, as in there's some vector here, which we are taking to be as perpendicular to all of the other points which fall on this plane. Let's call the vector of this normal theta. Additionally, this plane has an offset from the origin. So it's over here, O prime. This is O. And this is its offset. Let's call this x hat. So now we want to find all of the lines, all of the points which fall on this plane. So if we take another point, x, it will only be on this plane if its vector is perpendicular. Draw it over here. If its vector is perpendicular to theta. So we can write it like this. So this vector here is going to be x minus x hat dot theta is equal to 0. So x dot theta minus x hat dot theta is equal to 0. This is always going to be a constant. So we can just define our plane as all of the points which satisfy x dot theta plus some offset, theta 0, is equal to 0, where these two are defined to be equivalently. And this is the definition of our plane. So any point which satisfies this relationship, this linear relationship, lies on this plane.
Hi, in this video I'm going to talk about the loss function, gradient descent algorithm, and some tools on how to compute the gradients. The basic tool that we will use very often is the chain rule. Now the first two topics will be covered later on in the lectures, and here I'm just giving you some basic idea and some intuition about the things that we're going to talk about. Okay, so loss function. The loss function is some way for us to value how far is our model from the data that we have. Okay, so let's look at some simple linear regression model, which is just a model that we can look if we have just one-dimensional data like this. Okay, we have some input value x, and we use some parameters theta 1 and theta 2, which we want to learn in order to predict some y. Okay, let's say, for example, if we want to have a use case that x is the height of some person and y is his shoe size. Okay, so let's say that we start with the model, and now we have some data points that are something like that. Okay, obviously our model can be improved, and we want to learn the better parameters for theta 1 and theta 2 to better describe our data. So how can we do that? Let's first define the error. Now the error can be defined in many ways. Let's, for example, say that we take it as the vertical distance between our prediction to the real value. Okay, so if we write this as an equation, our loss function based on x and y will be just the vertical distance between the 2 points. Okay, this is for one example from the data, but we can actually take a set of examples and then take the mean of them. Okay, and this is actually is this, right? Okay, now we will learn about actual loss functions that are being used, and don't worry about it, we'll see many more. But now let's, for example, say that we have some kind of loss function that looks like this, where here I mean that this is the theta and this is the value of the loss function. Let's say that this is theta 1. So given this loss function, now for specific parameters that I have, I can say that right now I'm on this place on the graph. And what I actually want to do is to minimize the loss function, right? If the loss function is minimized, it means that my model best describes the data. Okay, now in simple cases, I might just solve it directly and find the minimum of the loss function. But many times our models will be very complex and we'll have a lot of data, and actually what we will want to do is to use some iterative algorithm. Okay, and the most common algorithm to use is the gradient descent. The gradient descent is actually a very simple concept. What we will do is we will take the loss function that we get from from our current set of data points. We will compute the gradient. The gradient is just the derivative of the function in this point, and we want to move against the direction of the gradient. Okay, so if it's here, we want to move a bit here, and we'll get to this point. Okay, so if we write it down, the update steps of the gradient descent, this we will want to find a new value for theta, which is the old value minus some gamma times the gradient of the loss function. Okay, and this gamma is what is called the learning rate. If it's very high, then we might move like this and diverge, and if it's very small, we might converge very, very slowly, or if our loss is actually if we have some local minimums, we might be more prone to get stuck in them. Okay, this is about the loss function. Sometimes it's been called the cost function or the risk function. It is all the same. Okay, now let's talk a bit about how to compute gradients. So our models will many times be pretty complex functions. Let's take, for example, let's say that our prediction, our model is something like that. E to the minus theta x plus theta 2. Okay, so now we want to derive that, let's say, in terms of theta 1. Okay, so what the chain rule tell us, let's write it down here, that if I have some function that I want to derive according to x, I can actually derive it like that in part. Okay, this is all. So if I want to derive this function now, I can actually write something like this. Okay, and what is this z? So I will define z just to be this part of the equation. Okay, and now actually I have this like a linear formula, and on top of that I have this more complex function, which is actually called the sigmoid function, and we will see it later on in the class. Okay, so I can actually look at my model as if I'm getting some input x, then I'm applying some linear transformation on it, which gives me z, and then I'm applying the sigmoid function to get my prediction. Okay, so now all we need to do is to solve those two derivatives. Okay, now obviously let's first do actually the dz. Let's start with a very simple one. dz to d theta 1, which will be only x. And now I need to compute dy to dz. Okay, so actually what I want to compute now is this guy. Okay, and this is actually, as I said, is a sigmoid function, and you can compute it yourself, but what you will get is that the derivative is this, minus z squared. Okay, so now I can just put those things together and use the chain rule to get my final derivative. Okay, it is just x times the sigmoid derivative squared. Okay, now I can plug in back z and to get my derivative. Okay, and if I want to do the same things for theta 2, then it's simply this thing. One plus, yeah. Okay, so this is the chain rule, and this is a very useful tool to derive more complex functions, and we will surely need to use it for deep learning later. And that's it.
Hello, and welcome to 686x. This introductory module serves to go over the NumPy library for Python 3, which we'll use extensively in the course. NumPy allows us to do complex computations involving multidimensional arrays and matrices, generate randomness, and also perform more simple functions we encounter every day. NumPy will serve as a sort of Swiss Army knife for math as we go through the course. So let's go ahead and tackle this through an example. One of the things we'll be using NumPy for in 686x is neural networks. And what I'd like to do in this tutorial is give a basic introduction to them and motivate them with NumPy. Now don't worry if you've never heard about a neural network before. They'll be covered in the course and you're not expected to know anything in advance. Fundamentally, a neural network is a system that looks like this. It's modeled after our own biological brain cells, or neurons, taking in signals and turning them into a useful output. In this case, our signals, our input, is right over here, and our output is right over here. We'll call our inputs x's, x1 and x2, and we'll call our output z. The way a neural network works is it takes in a few inputs and turns them into some useful output. And the way it does it is by weighing different inputs differently. These weights are captured by the variables w1 and w2, and what they speak to is the importance of x1 and x2 in regard to our output. The output of our neural network takes these inputs and these weights in the following way. It will weigh input 1 by weight 1, add that to input 2 times weight 2. And so this is the weighted sum of our inputs, and it will then perform some function. Now the function that the neural network applies is typically a nonlinear function such as the hyperbolic tangent or the logistic or sigmoid function. For the purposes of our brief tutorial, I'm going to go ahead and say that we're going to use the hyperbolic tangent, or tanh, on the weighted sum of the inputs. For the moment, this is all we'll need to think about. The course will teach neural networks from the ground up in the modules ahead. Now, where does NumPy come into play? NumPy comes into play in the representation of our inputs, our weights, and our outputs. Our inputs x1 and x2 we can visualize as a matrix. We can have a column matrix called X, which contains x1 and x2. Similarly, for our weights, we can have another column matrix W, which contains w1 and w2. And so we're taking this and we're representing it in a nice little matrix formalism there. So let's now take what we've covered in our fundamentals of a neural network and apply this in with NumPy. So I'm going to go ahead and move into the shell. And to use NumPy, the very first thing I need to do is import it. So I'm going to type in import NumPy. And typically we import NumPy with some shorthand, such as NP. By doing this, the number of keystrokes I need to call NumPy at any given moment is greatly reduced, make life much simpler. Now the fundamental unit in NumPy is the NumPy array, which is a matrix, and is based on traditional Python lists. For example, if I made a list in Python containing 1 and 5, that's quite handy. It stores the numbers 1 and 5, but there's very little I can do with that. It's very difficult for me to perform math on a Python list. For example, if I wanted to take x and add 1 to every element within, it wouldn't quite be so simple as x plus 1. With NumPy, however, life is greatly simplified. What I'm going to do then is redefine x as a NumPy array. And the way I do this is with np, or NumPy, dot array. Now x is a NumPy array with elements 1 and 5. I can do all sorts of things with this, among them operations. Like we said earlier, x plus 1, I get in 2 plus 6. X plus 2, I get other things. I can do x minus 4. I can do x times 5, and it does element-wise multiplication. NumPy fundamentally works like math, which means it's fairly simple to bring to it your mathematical intuition. I can also define another NumPy array, so I'm going to make a matrix y, and it's going to be np.array, and say I want it to have elements now 5 and 6. So here's y, here's x. I can do x plus y. I can do x times y. This gives me an element-wise multiplication. And I can also do x over y, which is an element-wise division. NumPy also contains methods for making particular kinds of matrices, such as matrices of zeros, ones, and even random matrices. For zeros, we have np.zeros. So if I type in np.zeros and feed into it a two-dimensional list which will contain my number of rows and my number of columns, I've now produced a 4x5 matrix of zeros. For ones, the procedure is quite straightforward as well. np.ones, 4, 6, for example. Now I have a 4x6 array or matrix of ones. NumPy also contains methods for making random matrices, and as we'll see later on in the course, we want to initialize our weights as completely random values. Now the way I do this is via np.random, which contains several functions, including random again. np.random.random allows us to produce a random matrix with a particular number of rows and columns. In particular, here I'm going to make a 3x2 NumPy array of random elements. This gives me elements drawn from the uniform distribution between 0 and 1. So in particular, for this neural network, if I wanted to initialize these two weights randomly, I might do something like np.random.random 2 by 1, give myself a column vector, and I'm set. Beautiful. Armed with this, you should be set to take on the first exercise, which is coming right up next. Now that we've gotten some practice with the basics of NumPy, I'd like to go into some more detail on NumPy array methods and attributes. And the first thing I'll do to get us started there is to define a NumPy array. Now, you remember earlier I've imported NumPy as NP, which means I can continue to use that shorthand all throughout. And so I'll say x is NumPy dot array, and I'm going to make a very simple two-element array with elements 3 and 5. Beautiful. So if I show x now, I have a NumPy array with elements 3 and 5. And among the things that come to mind when I think of a matrix are its dimensions. And accessing the dimensions of a NumPy array is actually very straightforward. To do this, we'll use x.shape. This brings up that it is a two-element array. Now, if we had a multi-dimensional array, for example, if I had here a 2x3 NumPy array, I've now got a 2x3 NumPy array. And I can prove this by going into its shape, just as I did for our x array. I'll type in y.shape, and that comes 2x3. And so shape is the way we typically access the dimensions of any NumPy array. An additional manipulation to matrices that is often done in mathematics is the transpose operation, whereby we take a matrix and we switch its rows for columns and its columns for row, fundamentally flipping the matrix. For instance, if we went to our NumPy array y, we would be turning this from a 2x3 matrix to a 3x2 matrix, where the rows and columns are flipped. And this, just as finding the shape of an array, is very straightforward. In NumPy, I need simply type in y.transpose. You see now that I have a 3x2 NumPy array. And if I'd like to check that, I can always set that equal to something, and then have a look at its shape. And indeed we see that we have ourselves a 3x2 matrix. Addition and subtraction of matrices works just like we've come to intuit from math. What's particularly interesting, however, is the way NumPy handles multiplication. Now, if we've got a matrix y, and say I come up with a second array, z, which is y plus 3, just to give ourselves a second array, I know that I can multiply these as follows, z times y. What this performs is element-wise multiplication, Traditionally, NumPy will perform element-wise multiplication. However, there will be times when one will want to perform traditional algebraic matrix multiplication. For this, NumPy has built-in np.matmul. Now let's recall that to be able to multiply two matrices, the number of columns in the first matrix must be equal to the number of rows in the second matrix if we're multiplying them in that order. If we satisfy this condition, we can place these two matrices into the numpy.matmul method. Now let's recall that originally I had a NumPy array X, which was a 1 by 2 matrix. So I'm going to bring in Z, which we know to have precisely this, 2 rows. Now performing a matrix multiplication would be as simple as np.matmul, X, Z, and out comes algebraic matrix multiplication. And as expected, if we're multiplying a 1 by 2 matrix by a 2 by 3 matrix, the result will have 1 row and 3 columns, and here we are. The final set of functions built into NumPy that I'd like to go over are functions that we've seen all throughout math. Sine, cosine, tangent, exponentiation, you name it. They work wonderfully with NumPy arrays. So let's go ahead to X, which I've already instantiated, and what I'm going to do is exponentiate the elements in X element-wise. Let's recall this is X, and so I'm going to say numpy.exp X. What this will do is raise e to each of the elements in X. This is wonderfully convenient because we don't have to write any backend to do this element-wise. NumPy takes care of it completely for us. Additional functions we could do this on include np.sine. Plug in np.sine of X, it would give me the element-wise sine, cosine, and tangent work the same way. Originally, we had also spoken about the hyperbolic tangent, among other things, and we can do this just the same way. np.tanh of X returns the element-wise hyperbolic tangent of each of the items inside of the NumPy array X. It may be worth recalling that in our initial conversation on neural networks, we talked about how the weights and the inputs are represented as NumPy column matrices. This may be worth keeping in mind to put into context what we've learned about transposing and multiplying matrices. Excellent. So in the coming exercise, you'll be able to get some practice with some of these features right before we move on to our final segment. All right, welcome back. What I'm going to do now is discuss a final set of features of NumPy that will serve you well coming up in the course. I'm going to begin by initializing a NumPy array. I'm going to go ahead and call it X as I have been. Let's say X is numpy.array, and it's going to contain elements, let's say 4, 2, 9, and -6, let's say 5, 11, and 3. Beautiful. So now I have instantiated a NumPy array, and I may want to figure out the highest and or lowest elements in the array. Now NumPy has built-in functions for precisely this. I need simply type np.max of X and np.min of X. Alternatively, I can access the maxes and mins from an array simply by looking within its attributes. If I type x.max, so we see that it's a built-in function of the NumPy array, meaning I can call it and retrieve the maximum element in the array along with the minimum element of the array. And so np.max or numpy.max and the particular array.max work in the same exact way, just as with min. The next thing I'd like to do is talk about two very important modules within NumPy, and they're random and linear algebra. Let's start with random. And to do this, I'm going to go ahead and type in np.random. And if we go ahead and type in dot and have a look at all of the methods and attributes within, we find a vast set of things we can do. In particular, I'll talk about generating a random matrix. So I'm going to go ahead and type in np.random.random once more and feed it in a size. I'm going to say I want to make a random 2 by 1 NumPy array. This produces a 2 by 1 matrix with elements drawn randomly from the uniform distribution. I can make arbitrarily large arrays as well if I'd like. np.random.random once more, 5 by 6 say, and now I have a 5 by 6 randomly generated NumPy array. I can also produce one element at random by simply typing np.random.random. I'll have a number drawn randomly from the the uniform distribution, in this case 0.9556. All right, and the second module I'd like to talk about is NumPy's built-in linear algebra module, and I can access it via np or numpy.linalg. Just as with random, there is a vast set of methods and attributes within. And in particular, I want to talk about finding the norm of a matrix, which is built into NumPy's linear algebra module as well. Now let's recall our NumPy array X. I now want to find its L2 norm, that is, the square root of the sum of each of its elements squared. The way to do this is np.linalg.norm of X. And this returns 17.08, which is approximately the square root of 4 squared plus 2 squared plus 9 squared plus negative 6 squared, so on and so forth. All right, with this you should be set to tackle the next exercise and then take on Project Zero.